Welcome back. Good morning. I'm Jason Hellenrung with Sasaki Associates, and we're happy to be a sponsor of the conference and be here this morning. Crystal talked a little bit about preparing for the Rising Tides 2 coming out, so we've been enjoying collaborating with them. Thank you to all of our speakers in the first panel this morning, and we've got an interesting segue here. I'm with Sasaki, and we just wrapped up our exhibit Sea Change, which was at District Hall. I recognize a lot of people here that I know have visited the exhibit. And we have outside, and I have with me some postcards, so all of the materials from the exhibit are online on our website. There's a link, so if you'd like to see that, come take a look. That looks at some of the vulnerabilities to sea level rise in Boston and strategies for the future. And so looking at that last panel, which was looking at finance and insurance and regulation and policy dealing with sea level rise and climate change, our next session starts to look at strategies for the future. So it looks at natural systems and green infrastructure systems and the role of landscapes and natural systems and green infrastructure to help alleviate some of those impacts of sea level rise. We have a number of great speakers this morning, and I'll give a couple quick intros. First, a little bit of housekeeping. In terms of questions, remember that we have our note cards, so please feel free to write down notes, and we'll collect them before our Q&A session at the end. Second is please silence your cell phones and mobile devices. And third, if you're an architect or planner, please remember to go outside and sign up because you can get credits for our sessions this morning and this session right here. So with that, I'm going to start turning things over to our speakers. And our first speaker of the morning, let me find my notes, is Dr. Jeffrey Donnelly. Jeffrey is an associate scientist with tenure at the Woods Hole Oceanographic Institution out on the Cape. And he is also an adjunct professor at Brown, and he is working in geology and geophysics. The focus of his research and the overarching goal of that is to understand how climate variability changes tropical cyclone activity, alters sea levels, and affects water availability. In addition, he seeks to understand the impacts of changing climate on terrestrial and coastal landforms and ecosystems. He's going to be talking about the perfect storm, the collision of tropical cyclones, climate change, and coastal population growth. Please join me in welcoming Dr. Jeffrey Donnelly.
Good morning. Well, before we look to the future, I'm going to take you into the past and a little bit into the deep past, actually. One of the things that we've been trying to do is to assess tropical cyclone risk by going back deeper in time than we can go with instrumental records and historic records and actually use geologic proxies to go back. But before we get there, we're going to go to the future. Well, let's actually start with the present. So here's what the instrumental data set looks like for tropical cyclones in the North Atlantic. And you've got 1850 here to 2010. And you can see that there's this increase in the overall frequency of events, including the overall frequency of the major hurricane events. There's a lot of controversy about this record. Our ability to observe these storms through time has changed dramatically. You can imagine back in the early part of the record here, we're only actually recording the storms that are making landfall where there's somebody there to record it. Or it happens to intersect a ship at sea. And obviously the other end of the spectrum is the modern day where we have satellites monitoring every inch of the globe. So there's some question as to whether this trend is real. And that's one of the things that motivated the proxy work to try to extend the record much deeper in time. And so now we'll go to the future, thinking about what might the future hold in terms of tropical cyclones. And there's still quite a bit of scientific debate about what the response of tropical cyclones to the warming climate is going to be. This is a figure that sort of points to the very high degree of correlation between sea surface temperature changes here in blue and the tropical cyclone activity in the North Atlantic. And if we look to what some of the future models are telling us, this is a result that came out of an analysis using Kerry Emanuel's model here at MIT, looking at various scenarios from some of the IPCC AR4 models. And what we did was chose a best case scenario out of his modeling suite, which was this ECM model, and then a worst case scenario. And this is going out, this is comparing it to modern, or basically the last 2 decades of the 20th century. And then these are going out 200 years, basically. But you go out 200 years with this, what was supposed to be a best case scenario, so it's still not a very encouraging scenario in the sense that there's nearly a doubling in activity, including the major hurricanes that are sort of menacing the eastern seaboard. And then the worst case scenario, you're getting closer to a tripling of the rate. Now, Kerry has just done a new analysis of this using the new IPCC model results. This is displayed a little bit differently, but you can see here is this track density plot. Globally, that this is a consensus of 5 different GCM runs. And you can see that the big loser in this is the western North Pacific, but we don't fare too well either here in the western North Atlantic, where we see an increase as well. And so there's a lot of regionality to this. Some areas are big winners and some areas are big losers. And one of the most interesting things I think about Kerry's new work is that rather than just going out 100 years or 200 years, he actually did this analysis on a decadal level. And it's not this sort of doomsday 2100 scenario where that's when we see all the increased activity. In our lifetimes, in the next few decades, we should be seeing a measurable increase in tropical cyclone activity based on this modeling result. Of course, the other thing that's going on is sea levels rising. This is a figure out of that new IPCC report where we have these proxy data that reconstruct sea level back centuries and millennia that show fairly slow levels of sea level rise. And of course, we've got this acceleration that's occurred beginning in the late 19th century until today. And then these are the projections, the latest projections from the IPCC. So we're looking at close to potentially a meter of sea level rise, by 2100. All right, well, I'm going to use Sandy as a vehicle to sort of talk you through this. Sandy was a very weak hurricane, actually, a marginal hurricane when it made landfall in southern New Jersey. What was unusual about it was large size. It was a very large tropical cyclone. The other thing that was unusual about it was its track. This is a SLOSH simulation. SLOSH is a model used by NOAA to forecast, but we've used it here in sort of a hindcast mode. And it's a fairly simple model, but it does a reasonably good job of capturing Sandy. You can see Sandy comes up, takes this turn right into the Jersey shore here. It's got a very large wind field, and it results in fairly high amounts of surge across this entire domain here, looking at something of the order of 6 to 8 feet of storm surge. And as I said, one of the things that was pretty unusual about Sandy was this track. And I'm going to show this relative to all the other tropical cyclones that have impacted the Northeast over the last several hundred years. And you can see it's really an anomaly. Almost all the other storms are basically tracking from south to north. The red here are Category 3 storms. The black are Category 1 and 2 storms. There's only one other storm that sort of takes a little bit of that same sort of recurve into the coast, and it hit almost the exact same location in New Jersey in 1903. I'm going to focus on the last Category 3 storm to actually strike New Jersey and New York City, this 1821 storm. It'll provide some historical context in sort of terms of, well, what was Sandy relative to what's possible. And again, this is a SLOSH hindcast simulation of that 1821 hurricane. It's sort of a best fit to the available data. And so it represents the best fit out of probably about 50 different model runs. This storm is actually pretty famous in the scientific community because it was the first time a Westerner was able to surmise that a hurricane was actually a rotary wind system. Until William Redfield here, we didn't really have any idea of the actual character of the storm. William Redfield was a merchant in Middletown, Connecticut, and took a trip right after the storm and noticed that near his home, all the trees had felled to the north, and as he moved towards New York City, they all had gone to the south. And from that was able to surmise that it was actually a rotary system. But you can see that the amount of surge here is pretty dramatic, all along the Jersey shore and in the New York Bight here. We were getting up to 14 or 15 feet of surge. This storm, very different from Sandy, not just in its track, but it's moving very rapidly. It's moving at about 40 miles an hour, and that's pretty typical for tropical cyclones at this latitude. Sandy sort of just really slow roll into the Jersey Shore at about 15 miles an hour or so, which is much more typical of a tropical cyclone at a lower latitude. So this raises some interesting problems in terms of getting people out of harm's way. This storm made it from the Outer Banks of North Carolina to New York City in 8 hours. So we don't have a heck of a lot of time. With Sandy, we had several days, an amazing forecast, close to a week out. Most storms won't behave that nicely for us and will be moving much more rapidly, and it'll be much more difficult to get people out of harm's way. So this is a comparison of those two. Here's Sandy, minimal Cat 1, and actually the Cat 1 wind field was restricted just to right around the eye of the storm here, close to southern New Jersey. The rest of the area was only experiencing tropical storm force winds. Then here's that track of the 1821 storm, and you can see dramatically different surge levels. So if we compare those, this is what the hydrograph would look like in downtown New York, right in the Battery and southern Manhattan. The yellow trace here is the storm tide. The red is the predicted tide that day. This is from the model simulation of 1821. This is actual data from the tide gauge. You can see that in 1821, they were extremely lucky. The storm hit at a dead low tide. Sandy, we were extremely unlucky, and it hit at a high tide. So that magnified the amount of inundation considerably. The other thing, the 1821 hurricane occurred on Monday, September 3rd. They weren't celebrating Labor Day then, but if they were, it would have been Labor Day weekend when the 1821 hurricane hit. So in terms of the absolute surge that the storm created, Sandy was a little less than 3 meters, about 2.75 meters, whereas the 1821 surge was closer to 4 meters. So if we put together a histogram of what that looks like for the Battery, here's Sandy in terms of, and this isn't the surge, but the actual storm tide, so it also has the local tide taken into account. Here's the level of inundation we get from Sandy. Here's a series of other historical events, including this 1821 hurricane. And then all this is from the tide gauge. Here's a bunch of winter storms. The event of record before we had Sandy was the Hurricane Donna here in 1960. And of course, things could have been much worse in 1821. Had it hit at high tide, it would have been more of a 5-meter storm tide. And we could have gotten lucky with Sandy. If it had hit a dead low tide, it would have been a fairly minor event. So here's the actual observations of that storm tide from the USGS collecting stations. You can see that most of it's here focused in the New York Bight, and some of it down here by the landfall. One of the things that we did immediately after the storm, because the reinsurance industry had actually come to us more than, well, I guess a decade and a half ago now. They got really hammered in Hurricane Andrew in Miami and Homestead, and realized that they didn't have very good statistics, and they got really worried about New York City. And so they sent us out trying to get these proxy records. What's the real risk for New York City? And so we went out and took a whole series of sediment cores on the reinsurance dime, and we're able to do a bunch of reconstructions. And this is what some of those sand layers look like in the coastal zone. This is from a back barrier salt marsh. You can see these really large overwash fans that was deposited by this 1821 hurricane. And so we went back after Sandy to try to put Sandy in context. And so we went back to all these same sites. Only one of them actually has an overwash fan. Even though all these other sites were clearly inundated, there was some human debris, stuffed animals, VCR tapes, stuff like that. There wasn't anything transported in terms of sediment. Part of that might be explained by us armoring parts of the coast, but every single site didn't have that sort of record, save this one. And this is what that looks like down Long Beach, New Jersey. This is pre-Sandy. Here's the one overwash fan that was deposited during Sandy. Of course, well, not of course, but amazingly, in less than 6 months after the storm, the owner of said new overwash fan, no longer wetland, was trying to sell the property for development for a modest $2.2 million. So it gives you some sense of the economic and social forces that are at play here. Of course, this isn't unusual. If you look at an aerial view of all these barrier islands, we've built all these communities on overwash fans. It's the speed at which this occurred that was the most surprising, that literally within 6 months of the event, like, people really do have short memories, although I don't know that he's actually been able to sell the property. Okay, so one question to ask is, well, Sandy was clearly a fairly big event for New Jersey, New York. What if it had taken a more typical track and been more of a southeastern New England event? And so all we've done here is take the same meteorological characteristics, same translation speed. All we've done is change the track and had it come straight up into southeastern New England. And this is what you get out of SLOSH anyway. You know, a reasonably high surge, about 4.7 feet here in Woods Hole, where the tide gauge is. It translates to about 1.5 meters or so. Nothing like what we saw in the New York Bight. If we try to put that in sort of a longer term perspective, here's the tide gauge record, or at least the monthly extreme record from the Woods Hole tide gauge. And so each one of these is a monthly data point. These are some of the bigger hurricanes in the middle part of the 20th century, 1938, 44, Carol, Donna. Here's Bob here. So these are the actual measurements for Irene and Sandy at the Woods Hole tide gauge. This would have been the level had it made a landfall in southeastern New England. So it would have been a significant event. Wouldn't have been as big as Bob. Would have been perhaps similar to what we saw in Donna in 1960, but really nothing like what we saw from 38, 54, and even some of these earlier historic events like 1815, 1635. So the basic message there is that it can get a heck of a lot worse than Sandy. So why so much damage from Sandy? And Cynthia hit the nail on the head earlier, so I won't beat it too much further, but we're clearly the issue. You know, this is what the Jersey shoreline looked like when the 1821 hurricane hit. We had some salt works, some fishing shacks, not much else. And then in the intervening century and a half, or almost 2 centuries, we've decided to build cities on these low-lying barrier islands. And this is what the coastal population has done since 1821. And then since the last, this is actually a Category 2 storm in 1893. And since then, New Jersey, New York has been really lucky in terms of hurricane strikes until Sandy. And it was a great time to buy coastal property. Of course, sea level is rising through this entire interval. Here's the tide gauge record in red from the Battery. This blue envelope here is actually a sea level reconstruction based on a salt marsh core from New Jersey, which basically mirrors that pretty well and extends it further back in time. So you can see since 1821, sea level's already risen 2 feet. So not only have we developed these barrier islands and put fixed infrastructure down, but they're slowly drowning. And as we saw on that first slide that I showed, they're drowning faster and faster. Okay, so now I'm going to talk a little bit about that long-term perspective, and it's not particularly good news. This is another simulation of the 1635 event, which is probably the most intense event to strike southeastern New England. And I put it up here as sort of an example. We've cored all these different sites along this stretch of the coast, and we find these big overwash fans in these environments from the 1635 hurricane event. It's these big overwash fans that are able to allow us to sort of extend the record back much deeper in time. And so here's, I'm going to show an example from Salt Pond, which is actually about 1 kilometer from my lab, but it turns out to be one of the more amazing reconstructions. And there's a real regional coherency to the record. So I'll just show that one. But this is basically how it works, where we go into these deep basins along the coast, take a core, and this is the sediment core, and it's basically a time machine, right? It's accumulating slowly through time, and these are old sand layers that were deposited by ancient hurricanes that we're able to use to reconstruct the history. So here's what that looks like when you look back 2,000 years. Here's the modern 2000 AD, going back 2,000 years. These are those overwash layers, and they're basically the amount of sand that's deposited in the core through time, if you will. You can see that the most recent few hundred years when we settled and then developed the region, it's been fairly quiescent. This first event here is Hurricane Bob in 1991. None of those mid-20th century events are recorded this far east. We got to get on the other, into Buzzards Bay and the other side of Buzzards Bay, moving west to pick up the 38 hurricane, the 54 hurricane, Hurricane Carol and whatnot. There's this big pulse of activity here, starting at about 1450 AD until the 17th century, another quiet interval, and then this interval back here where it's very active, at least in terms of, excuse me, the really big events, the events that were able to transport much more sand into these environments. And so I won't sort of go into all the details here, but we've done some frequency analysis. And so what we're looking at here is there's intervals in the prehistoric past where you're looking at events that are approaching sort of 4 or 5 of these catastrophic events per century, much bigger than what we saw with Bob in terms of at least their ability to transport sediment. So very different frequencies. So what this means is that the climate system, without our intervention, is already capable of producing tropical cyclone climates much greater than anything we've experienced in our lifetimes, which is fairly frightening. I mean, you know, we've sort of, from the climate models, have been able to surmise that, yeah, we know sea surface temperatures are important for driving tropical cyclones. We know we're warming them. The models seem to point to more activity, but here it is. We've got the climate system naturally being able to sort of produce it itself. And it turns out that these active intervals, this active interval here and here, are ones in which there's a sea surface temperature, a warm sea surface temperature anomaly off the eastern seaboard of the US. And then this interval here, so these two intervals, it's only really active on the eastern seaboard of the US. When we put a composite of all these reconstructions we've done over the years together, it's only the eastern seaboard that's active in here and here. In this interval, the entire basin's active. So it's the Caribbean, it's the Gulf of Mexico. It's the eastern seaboard that's active. It turns out this is related to a warm sea surface temperature anomaly in the deep tropics. And these are related to warm sea surface temperatures off the eastern seaboard. So sea surface temperatures matter, and they matter in a big way when you start looking at these longer time scales. So let's talk a little bit about landscape impacts, because that's sort of the session theme here. And I won't go into these, into the sort of future mitigation sort of aspects, but provide, again, this sort of long-term perspective. When we start looking at what happens to the landscape during these really active intervals, it's pretty interesting. This interval here, as I said, between about 1450 AD and the middle part of the 17th century, is one in which the Outer Banks of North Carolina is getting carved up. This is the frequency of inlet formation in the Outer Banks that a group from North Carolina put together. You can see that during this active interval, when you're getting many, many more hurricane strikes on the Cape, you're getting inlets torn through the Outer Banks like crazy. That's obviously going to change your flood protection. It's going to change your ecosystem. The good news is the Outer Banks is still there. It's survived. It's sort of put itself back together. But that interval, when it was really active, it was a very different system. It would be much more porous to storm surge events. The other thing that's going on apparently during these active intervals is that salt marshes are bearing the brunt. This is a reconstruction that was done from coastal Connecticut. This is a cross-section, so I'm a geologist. I sort of think in cross-sections a lot. But this is a study done by Orson van de Plas, who goes out and takes 500 cores from a salt marsh, and was able to do these really detailed reconstructions. And what he found was that there were huge chunks of the marshes missing, and was able to date them fairly precisely. And it turns out they're dating to when this active interval is. And this particular one he attributed to the 1635 hurricane event. And so here's a map of that salt marsh. It's one of these classic drowned river valley marshes. And these black areas here are that's the material missing from a single event. These storms are having a really big impact on the landscape. And sum up here, North Carolina and New Jersey were really fortunate through most of the 20th century. They didn't see any really big hurricanes. Unfortunately, that was a time of unprecedented development. One could argue that Boston and New England have been pretty fortunate, except for that short, few decades in the middle part of the 20th century. And this is part of the worrying thing here, is that apparently storms much greater in intensity than Sandy or Bob have impacted the area historically and prehistorically. And over the last 2 millennia, there's been unprecedented intense hurricane activity, where you go from thinking of an event once every 100 years in the Cape, once every 200 years in New York. Suddenly you're looking at events that are occurring once every decade, you know, a couple times every decade in a few cases. So it's a very different regime. And these active intervals are related to intervals of elevated sea surface temperatures, which is exactly what's going on today. We're increasing the sea surface temperatures. The impacts are going to be exacerbated by sea level rise and coastal population growth, even regardless of what happens with the hurricane. Even if we don't see a doubling, we're still in trouble. We've put Atlantic City at sea level, fixed its infrastructure, it's slowly drowning. Even if we keep the storm climate stationary, we're still in big trouble. And then this final point, or next to final point, I think, is that it's these active intervals of sort of unprecedented levels of activity seem to have pretty big impacts, at least on the short term, to the landscape. We didn't see a lot of that sort of damage during Sandy, mostly because I think it was a minimal event, but there were some created wetlands that were just completely ripped up. They just weren't resilient to even a Category 1 hurricane. So it's something you need to think about if you're engineering to create a wetland or to restore a wetland. How resilient might it be to, you know, something like the 1938 hurricane or that 1821 hurricane? And so the final bit there is that at least during these active intervals, you might see some loss in the protective services that these landforms provide in terms of flood protection. If you get lots of breaches in your barrier, it's going to allow a lot more surge to get through your barrier into the developed upland behind it. The marshes are going to degrade, at least temporarily. The good news, again, the marshes are still there. They were there 4,000 years ago. They're there today. But there was an interval there where they were completely torn up. And so they're not only their flood protection services, but their other ecological services will be compromised potentially. And I'll finish with a series of photos from downtown Providence from 1954-38 and a painting that was done in the 1815 gale. And you can find more information at our website if you're looking for it. Thanks.